Good day and welcome back for the third part of our discussion on how derivatives affect the shape of a graph. In our previous videos, we've introduced what the first and second derivative tests tell us about the shape of a graph, and also how we can use them to classify critical points as a local max, local minimum, or neither. So to start off this video, I just want to give a quick reminder of these key facts that we will make frequent use of. So recall that the first derivative tells us something about a function being increasing or decreasing. So if the first derivative is positive, the function is increasing on that interval I. If the first derivative is negative, the function is decreasing on the interval I. Similarly, a second derivative is going to tell us something about concavity. If the second derivative is positive on an interval, then f is concave upward on I. And if the second derivative is negative, that indicates that the function is concave downward. Also, let me remind you that once we know something about where a function is increasing or decreasing, we can apply the first derivative test to determine if a given critical point will be a local maximum, local minimum, or neither. And let me just draw each example out individually. If we happen to have a local maximum at C, we could see that in the first derivative because the first derivative is going to be changing at C from positive, an increasing function, to negative. So if you go from increasing to decreasing at a critical point, it must be a local maximum. And we could write this out in words, but I'm not doing that because I think the graphs and the intuition tells us everything that we need to know. If you happen to have a local minimum at C, note the function is going from decreasing to the left of C to increasing to the right of C. That is, the first derivative changes sign from being negative to positive. And lastly, it is possible that you could have f prime of c equal to 0, but there is not a local maximum or minimum. In this case, it's because f prime does not change sign. You are increasing as a function to the left of c, and you continue increasing to the right of c. We can similarly make this observation by investigating the second derivative. So by the second derivative test, which I will almost always abbreviate with an SDT, if you have a critical point at C, and it corresponds graphically, say, to a local maximum, this will occur precisely when the function is concave downward. So the second derivative is negative. Similarly, if you happen to have a local minimum at C, this corresponds precisely to the graph of the function being concave upward, which means the second derivative will be positive. And now that we've made it through our reminders, let's go ahead and put this all together in a single, very common type of an example that we will encounter. For the function 2x squared divided by x squared minus 1, we would like to work our way through 4 steps. Let's determine the intervals of increase and decrease by investigating the first derivative. Use that first derivative test to classify our critical points. Use the second derivative to find the intervals of concavity. And then take all of that information in steps A through C and see if we can use it to put together a rough sketch for the graph of this function. So the first step in part A requires us to differentiate the function. And to differentiate, we will use the quotient rule. And I'll just talk our way through this in words. We take low d high minus high d low, all divided by the bottom squared. And then if we go ahead and simplify, we see in the numerator the 4x in that first term needs to be distributed, making the first term a positive 4x cubed, which is exactly what you are subtracting away in that final term. And f prime x simplifies, and we end up having minus 4x over the quantity x squared minus 1 quantity squared. And what we would like to know for f prime of x is where is it equal to 0? Because recall, once we find where it's equal to 0, then we can then investigate what happens in between. So note, a fraction is equal to 0 precisely when the numerator is equal to 0, which occurs only when x is equal to 0. And I will come back to this formula for f prime in a moment, but for now, we need to make our sign chart for f prime. That is, we want to know where will f prime be positive, where will it be negative, and this value of x equals 0 corresponds to a potential location where f prime might change signs from positive to negative. But note, there's another way f prime can change sign. It's not just where the numerator is equal to 0. F prime could potentially change sign when the denominator is equal to 0 as well. So this is something that's a bit more subtle, but it's worth pointing out as it will come up again with the second derivative as well. So just note, f prime can change sign where the denominator is 0. So it's not guaranteed to change sign, but it's a potential location. So in this case, the denominator is equal to 0 when x squared minus 1 is 0, or x is equal to plus or minus 1. And note, these values of x equals plus or minus 1 is where the function f is undefined, and you actually have a vertical asymptote in the graph. So it does make intuitive sense that the function behavior could be different on either sides of plus or minus 1. And that gives us 4 potential intervals to investigate in terms of increase or decrease of the function f. Now, f prime actually has a fairly nice formula to work with. It's minus 4x over x squared minus 1 squared. And as we have done previously, we could easily pick a single point in each of these 4 intervals, test the sign of f prime, and use that to determine what's going on. But in this case, it's actually even a bit simpler because the quantity we have in the bottom is a square, which means it's always going to be positive. So all we need to do is really investigate what's happening in the top. This minus 4x will completely determine the sign of f prime. And lucky for us, that's an easy quantity to work with. For minus 4x, if you substitute in x as any negative quantity, so think anything to the left of 0, minus 4x is going to be positive. And what that will indicate is f prime will be positive to the left of minus 1 and in between minus 1 and 0. If you happen to substitute in any positive quantity for x, minus 4x would be negative, which indicates to the right of 0, f prime will be negative. And this immediately determines for us the intervals of increase and decrease. So our function f is increasing from minus infinity to minus 1 and from minus 1 to 0. It's decreasing from 0 to 1 and from 1 to infinity. And I'll note, if you happen to combine that all together and make just a single interval for increase and a single interval for decrease, it's not 100% correct because this function fails to be defined at plus or minus 1, but I would understand what you're saying and that would be okay. It's just preferable to kind of break it up as we've done in this case. And note that in order to determine these intervals of increase and decrease, our starting point was to really think about where that first derivative is equal to 0, which allowed us to determine that there is a single critical point at x equals 0. And looking at our number line above, for that critical point at x equals 0, the first derivative is increasing to the left of the critical point, decreasing to the right. So that critical point is going to be what? A local max, a local min, or neither. And drawing that little graph above the critical point at 0 tells us exactly what's going to happen. There is a local maximum at x equals 0. And I'm also going to note, I'm going to add a little bit of extra information at this point. When we get to the fourth step and we want to sketch the graph of this function, it's helpful to have a couple key points. So let's go ahead and find the corresponding point on the curve. So f of 0, if we substitute into f, would be 2 times 0 squared over 0 squared minus 1, which is equal to 0. And this gives us a specific point that we can work with on our curve, 0, 0. And that point 0, 0 corresponds to a local maximum. So now moving on to part C, we will determine the intervals of concavity. And to determine the intervals of concavity, this requires us to find the second derivative. So looking above, we see the formula that we have for f prime. We would once again need a quotient rule to differentiate and find f double prime. So just talking our way through this quotient rule, we would take low d high minus high d low. And note, when you differentiate this function in the bottom, it requires a chain rule. And the chain rule tells us that we are going to differentiate the outside function, substitute in the inside function, and multiply by the derivative of that inside function. And then everything is being divided by the bottom squared. And note, if you square a square, it becomes a fourth power. So as we've indicated earlier on, we do want to make sure that we are quick and efficient with our differentiation skills because they are now a smaller part of this larger problem. So in order to simplify, we're going to do something that's a very common technique. We're going to cancel off anything common to every term. Note, there's an x squared minus 1, an x squared minus 1, and an x squared minus 1. And just to make sure we don't do anything too silly, we need that x squared minus 1 to factor out of everything on the top. So I'm going to go ahead and factor that out, and then we'll see what we have remaining. So if we pull the x squared minus 1 out of the top, we know we'll have a minus 4 times a single x squared minus 1 remaining. So minus 4 x squared minus 1. In that second term in the top, if you pull out the x squared minus 1, what you would have remaining is minus a minus 4x times 2 times 2x. That is 4x times 4x, so plus 16x squared. So the single x squared minus 1 that we pulled out of the numerator cancels off one of those x squared minus 1's in the bottom. So note, this is just a slow, gradual process. We're not trying to rush our way through this. So taking this a step further, note that the minus 4 distributes through, and in the top we would have minus 4x squared plus 16x squared, which means 12x squared. And then to go with that, we also have minus 4 times minus 1, which is a positive 4. And we're dividing by x squared minus 1 cubed. And our goal now is to determine where that second derivative is positive and negative. So we need to go back to this number line technique. That is, where is the second derivative equal to 0? And note a fraction is equal to 0 precisely when the numerator is equal to 0. But note 12x squared plus 4 is never equal to 0. This has no solutions because 12x squared is always positive, plus 4 can never be equal to 0. But recall, that doesn't mean f double prime will never change sign. It can change sign when the denominator is equal to 0 as well. So similar to the observation that we made in part A, we can note that f double prime can also change sign where that denominator is equal to 0. X equals plus or minus 1. And that's what we have to be careful of. So we have minus 1 and 1, and now we need to test a point from each of these three test intervals to see if f double prime will be positive or negative. So let's just start off with a point in the middle interval. 0 is nice and simple to work with. So in this case, f double prime of 0, and note, f double prime is what we want to know about, so that's the function we substitute into. F double prime of 0 will be 0 plus 4 over 0 minus 1 cubed. 4 over minus 1 cubed is minus 4, which is negative. So our function will be concave downward on the interval from minus 1 to 1. And that leaves us with two more intervals to check. But I'm going to note we actually only need to check one of those intervals. If you look at the formula for f double prime, we have an x squared and an x squared. So for example, if we were to substitute in plus or minus 2, a test point from one of these intervals, you would get out the exact same quantity. So we'll just do it all at once. So let's just note f double prime, whether we substitute in plus or minus 2, it's irrelevant, would be 12 times 2 squared plus 4, all divided by 2 squared minus 1 cubed. And we don't have to overthink this at all. We can just note that what's in the top is positive, what's in the bottom is positive, and a positive divided by a positive is also positive. And that gives us two intervals where our function will be concave upward. And I do want to emphasize that these points plus or minus 1, where the numerator of f double prime equals 0, which were potential locations for f double prime to change sign, made a huge difference in this problem. They did not make a difference in part A, but for part C, they were very impactful. So we do have to be careful to watch out for those values. And now we have our intervals of concavity. And remember, this is just a smaller part of a larger problem, so I need you to write these out for me as clearly as possible. So we are concave up on the interval from minus infinity to minus 1, and 1 to infinity. We're concave down in the middle from minus 1 to 1. And I'll also ask you to circle kind of those conclusions that you're making. And if you look up towards the top of the page, you can see there's one small part remaining. We want to take this information and see if we can use it to give a rough sketch of the graph of the function. And as a reminder, the function f of x is 2x squared over x squared minus 1. And in order to put all of this information together, I typically will draw a small number line underneath my xy coordinate plane, and on that number line I'll just indicate the information that we've collected in our previous steps. So what we've seen in our previous steps is that the function is increasing whenever we have negative inputs, and it's decreasing whenever we have positive inputs. And then looking more recently at part C, we have our intervals of concavity. The function is concave upward to the left of minus 1, concave downward between minus 1 and 1, and concave upward after 1. And then we also saw in part B that we have a local maximum at the point 0, 0. And one last thing I'm going to add in is we know that the function f of x, a rational function, is undefined at plus or minus 1 because of dividing by 0, which would give us a vertical asymptote corresponding to x equals 1 and a second vertical asymptote corresponding to x equals 1. And I will also note, just for fun, this is an even function, i.e. all of the x terms are squared. And if you substitute in a large value for x, you will get back something positive. So roughly speaking, if we're between minus 1 and 1, we have to increase up to this local minimum and decrease, and we're approaching those vertical asymptotes. There's only one possible shape this graph could take on. Something that looks roughly like this. And then similarly, we know that if you're to the right of 1, your function is decreasing, and you have to take this vertical asymptote into account. And if you're decreasing away from it, it could only look like this. That is to say, the graph would roughly have to be something of this form. Similarly, if you are to the left of minus 1, you're increasing into that vertical asymptote, which will give you a shape similar to this. Now, the remaining question here, of course, is how do we know it really looks this way? Can we be a bit more precise? And the answer is absolutely, and that's really going to be a topic for our next section. But specifically what we might be interested in determining is what happens way to the right or way to the left. How can I be 100% sure what that curve is approaching? So before getting to that next section, we're at a perfect opportunity for you all to practice some examples. And as usual, you can go to Canvas and find an associated class worksheet. I recommend giving yourself a solid 25-30 minutes to work through these problems. They can be time consuming, they can be a bit tedious, but getting these skills and techniques down now will certainly aid us in our future sections. So if you have questions, let me know. Otherwise, stay tuned and take care.